Let's consider a Fourier series with an arbitrary period. So let's consider a function that repeats every 2 pi, for instance, a function here, and it has the usual Fourier series expansion. And the question we want to ask is, what about a function that doesn't just repeat every 2 pi, but let's say the function repeats every 2L, where L is arbitrary. So we'll just redraw the function here, and it's going to look exactly the same, except now it's repeating every 2L. So what is the Fourier series for this function? Well, notice that our original Fourier series, these cosine and sine terms, had periods which were 2 pi over n. So we expect that our period here might be 2L over n. So let's write a Fourier series expansion that does that. So we have a0 plus a sum over n, a sub n, and now cosine of n pi over Lx gives us such a period. And then we have similar terms for sine, n pi over Lx. Okay, so this could be an expression for a Fourier series with an arbitrary period. But what are the Fourier coefficients? The a0, a sub n, and b sub n. How do we find these coefficients? Well, we're going to use a trick that we used in a previous video, which is we're going to use orthogonality. We're just going to sketch the idea here. So in a previous video, we noticed that the integral from negative pi to pi, cosine of nx, cosine of mx dx, is pi delta mn, where delta mn is the Kronecker delta. What we want here is an integral from negative L to L of cosine of n pi over Lx, cosine of m pi over Lx dx. And we can make this look like the one above by doing a substitution. And after our substitution, our integral is an integral from negative pi to pi, cosine of nu, cosine of mu times L over pi du. Well, we can pull the L over pi out, and so then the value of the integral is just pi delta mn, the integral that we had above. Or really, the value of this integral here is just L delta mn. And so we have a new orthogonality relation for cosines with an arbitrary period. There's a similar expression that you can derive for sines, which I'll let you do on your own. So now we can write our function. Here's our Fourier expansion for an arbitrary period. Remember the n pi over Lx for the cosine and the sine terms. And now we can derive an expressions for a0, an, and bn. And again, I'm going to refer you to one of the videos on the derivation of those Fourier coefficients for your period of 2 pi, because the argument's pretty much the same. The expressions we get are a0 is 1 over 2L, the integral from negative L to L of the function. A sub n is 1 over L, the integral from negative L to L, of the function times cosine of n pi over Lx. And then a similar looking expression for the b sub n coefficients. Except now, instead of cosine, we're going to have sine, n pi over Lx dx. And please watch out for the n pi over L in those terms. Of course, these reduce to the usual period 2 pi results if you just let L equal to pi, which is a nice check. So let's look at an example. Again, the function that we've been considering above, so our square wave, which looks like this, and we want to find the Fourier series expansion for this function f of x. The first thing we need to do is determine how often it repeats, and so this repeats every 10, which means that 10 is equal to 2L, or rather L is equal to 5 here. Okay, so we can write our coefficient a0 as 1 over 10, the integral from negative 5 to 5 of the function. But the function's only non-zero between 0 and 5, and so we just get 1/2 for a0. An, we have a similar expression, integral from negative 5 to 5, f of x times cosine of n pi over 5x dx. And again, that's only non-zero between 0 and 5, but we end up getting 0 for the a sub n's. The b sub n's is a similar integral, except with a sine. In this case, you'll find that you don't get 0. In fact, you get 1 over n pi times 1 minus cosine of n pi. We could write that in a slightly more useful way. We could write that as 2 over n pi if n is odd, and you could check out 0 if n is even. So our Fourier expansion for this arbitrary period is 1/2 plus the sum on n's where n is odd, 2 over n pi sine of n pi over 5x. So now we figured out how to write the Fourier series for an arbitrary period. Now let's move on to a different topic, but somewhat related, which is making even or odd extensions of functions. So let me consider a function, or at least a part of a function here, that goes from 0 to 3. Looks something like this. Maybe this would be something like x squared plus 1, maybe. In fact, I'm just going to draw this fragment of the function. And I want this function to repeat, so I want it to be periodic. There's several different ways that I can make this function repeat and be periodic. Namely, there's several different ways I can extend this function to be periodic, because of course it's not periodic by itself yet. So let's sketch those different ways. So one way, here let me draw 3, 6, minus 3, minus 6. So here's my original fragment of the function. And so let me now extend this function in this way to be periodic. And this extension makes the function even. And when I extend it in this way, then it has a period of 6. And since it's even, then I only get cosines. I can, on the other hand, take my function, again in the same domain, and I can draw my original fragment here, and I can imagine extending it like this, so that my function is actually now odd. And so I would say this is an odd extension. This odd extension has a period of 6, and since it's odd, then I only have sines. Finally, I could choose to do neither even nor odd. So I could take my original fragment of a function and just have that repeat over and over again, like this. And so, of course, this is neither even nor odd. It's a combination of even and odd. Importantly, notice that this function has a period of 3. And of course, now since it's neither even nor odd, it will involve both sines and cosines. So, which should you use? How should you extend your function? Well, as with most questions like this, it depends. So all of these extensions, notice that they all give the same function in the original domain. So in the region between 0 and 3. So here, and here, and here, the function is all the same. And so it doesn't really matter if you just want to model the function in that area. For outside of that region, it depends on what type of function, namely an even or an odd function, that you're trying to model, and the type of period that you want for your function. And so that will depend on your particular application. And so you just have to make a decision and figure out which one suits you best.